Me as well. Okay, has it started? Okay, hello. Welcome to, I guess this is my first talk of the term. We've already had two from Daniel. Today I'm talking about a subject that I could have talked about at any point up to now. It's a really foundational differential topology result called the Pontryagin-Thom construction. It kind of is like the traction that this field gets to actually accomplish things algebraically, like relating geometry and algebra. In principle, it takes this structure called the Cobordism groups, and it realizes them as homotopy groups of some interesting family of spaces. And then people realize, okay, well, instead of thinking about this family of spaces, what if we construct one object that kind of encapsulates this type of family? This is where stable homotopy theory kind of grew out of. So really big ideas coming out of this very kind of basic fundamental thing. I'll start by just quickly recalling what is cobordism for people who aren't so familiar. It's a relationship between smooth closed manifolds. So remember, closed means compact and no boundary. Or the boundary is empty. It does have a boundary, it just is empty. So a closed means compact, empty boundary. And we say that these are related, and we'll call this relationship cobordant. If and only if there is a smooth and compact manifold which is one dimension higher, which sort of interpolates between these two manifolds. So specifically, we have embeddings of the manifolds into the boundary, so that the boundary is just the disjoint union of these two manifolds. So you can draw it like this. Here's M, here's N. Here's an example of a manifold going between M and N. This is everyone's favorite pair of pants, but maybe, you know, you ate some gnarly food and then there's a big hole in the back of your pants as well. So you can add interesting topology to these cobordisms. They don't have to be like minimal or anything like that. It just has to be some manifold that has the correct boundaries. Okay, and this is a symmetric relation as well, just by definition. If the boundary is M disjoint union N, it's also N disjoint union M. It turns out to be an equivalence relation. Yes, I'll leave it at that. So we can define this object omega n. I'm just taking to be the diffeomorphism classes of smooth closed n manifolds modulo this cobordism relation. By a result that we're going to mention a bit later, the Whitney Embedding Theorem, this is actually a set. Diffeomorphism classes of closed manifolds form a set because for each of them you can choose an embedding into some large enough Euclidean space. And so the space of all diffeomorphism classes is at most contained in the power set of this Euclidean space. So that's a set. So this makes sense to talk about the equivalence set. And I called it a group. Why is it a group? Well, we can add things together by taking their disjoint union. Diffeomorphism classes of closed manifolds. The interesting thing is that we actually get inverses once we introduce this cobordism relation. So in particular, if you take the cylinder on M, and you like bend it in half like this, on one end you get the disjoint union of M with itself, and on the other end you get the empty manifold. So two copies of M, since we don't have any extra structure, I'm not talking about orientations or anything right now, two copies of M are the boundary of the cylinder, and so everything in fact is two torsion. That's pretty interesting. Here's a pedantic note if you've never thought about this before. The empty set is a closed smooth manifold of every dimension. Every dimension. So, and in particular in our cobordism group, it represents the identity element. So if you take M, right, M disjoint union, the empty manifold, or what am I trying to say? Yeah, so if you take M disjoint union, the empty manifold, that this is cobordant to M itself just by taking the cylinder on M, right? Here's M, union the empty manifold. You don't do anything, the other end you have an M. So this is indeed an additive identity on this cobordism group. There are in low dimensions, you can do some ad hoc computations. For zero manifolds, of course, if you take two points, you can draw a line between them, you can connect them by a line. So 2 points, any 2 points is actually going to be cobordant to the empty manifold. And so since the only zero manifolds are points, and the only closed zero manifolds are finitely many points, You get a Z mod 2 just by counting the number of points mod 2. That's sort of like the easiest possible computation of these things. Omega 1, since we also have classification of one-dimensional manifolds, closed one manifolds are just circles, and the circle bounds a disk. So there's actually nothing going on in dimension 1 as far as cobordism is concerned.
But it also bounds the Möbius strip?
It does. So now you have two very good examples of a null bordism of the circle.
Okay.
That's not a contradiction. Yeah. Yeah, you can pick any manifold. Like I said, you can have weird, interesting topology. You just need some manifold that it bounds. Omega 2, things actually start to get a little bit more difficult. This is actually Z mod 2. The non-trivial element of this group is represented by the RP2. And the way that you distinguish this is through something called characteristic numbers, which I haven't really talked about at all. But they're very relevant to cobordism and doing computations in cobordism. But I'm not going to talk about that much today. I'm mostly going to be talking about this interesting geometric construction, not so many the algebraic computations. So in particular, all of the orientable 2 manifolds, we know that these embed in R3. They bound by the by the Alexander duality, I guess. They bound an interior region. So all of the orientable manifolds are boundaries. And the sort of simplest non-orientable manifold is generating this cobordism group for us. Omega 3, I actually didn't look up the value. I just said it's harder to figure out because I couldn't do it off the top of my head. There are many more 3-dimensional manifolds, and they do get more complicated. Yes, you can go and try to find a non-trivial one if you get bored. So one that's not null-bordant. And characteristic numbers are going to be the way to figure that out.
Are all these omegas known? So it's like omega 4 known or something? Or is
like if you wrote down like omega a million, is there a formula for it?
Yeah.
I think it's one of these cases where like there's a procedure for computing.
Mm-hmm.
In this particular, I said like atom spectral sequence.
Right.
I'm pretty sure, I don't remember off the top of my head, there should be like a final answer to like this is, okay, well here's a great observation. These all form a ring. So you can just add them all together. It's actually like a Z2 algebra. And so the atom spectral sequence, you can do a computation of like what actually is this ring. And so once you go and you want to pick 1 million, then you find like all of the homogeneous elements of degree 1 million.
So it is doable. It's not like it's an open problem. It's like, what's omega 5?
Yeah, at this point it is not an open problem. Yeah. So these were things that people thought about really, really hard in like the 40s and 50s. Yeah. So people like Thom, Wall, Pontryagin as well, they would have computed these groups like up to 18 or something like that, and then figured like this is starting to get ridiculous. We need to find something more systematic. Okay. Okay, so this is kind of the idea that we're revolving around is cobordism. So now I'm going to go through some of the basic differential topology notions that we're going to be using to talk about this computation. So we'll start with normal bundles. So if you've done div geo, if you've thought about like curves or surfaces in R3, you've thought about normal bundles. So any smooth function has a normal bundle. So let's call it F. So let's take a manifold of dimension M. No, don't do that.
No.
Then you can't see the board from here. Why are you doing that anyway?
Oh, more like.
Okay, well, if it's open, then like I can't read the board at least. Yeah, awesome, thank you. Yeah, Vaughn and I were like messing with the blinds just to try to make sure that the board was visible before everyone showed up. So don't undo our work, please. Okay, so any smooth function, when I declare my variables, when I declare a manifold variable, I put a superscript denoting its dimension. So I'm choosing to have the dimension match up the name of the manifold itself. So any smooth function has a normal bundle. And how does it work? So the fiber over some point P in M is going to be, well, what you could do is you could take the push forward of the tangent space at P. Now this is a subspace of the tangent plane, tangent space at Z, and you can just take the quotient by that. So here's a quotient space. It's basically, you're trying to pick a complement of this tangent space. And I'm pretty sure you can also just write this as like, pull back the tangent space over Z, and then you're going to be able to find out that this sits naturally inside of that, and you can take the quotient over M as well. So over here, if you write it like this, you're talking about bundles that are over Z. If you write it like this, you're talking about bundles that are over M. It's kind of like whichever you prefer. I believe these vector spaces are going to be the same. So if you have a metric,
But don't you need it as constant rank or something? Otherwise,
yeah. Yeah, then it's not a locally, yeah, then it wouldn't be, yeah, sure, okay, any smooth with constant rank, yeah, good point.
But sheets are okay.
Yeah, but I said bundle, yeah.
Yeah, fair.
Yeah, he's calling me a liar, it's okay. So if you have a metric, then you can do this differently. So we have a notion of orthogonal complement, and you can just do, push forward this tangent space, which if it has constant rank, then these all have the same dimension. And you just take the orthogonal complement in this larger tangent space.
Why do you want to push forward? Because I think the normal bundle should be a bundle on the domain, not on the target, right?
Yeah, it doesn't really matter if you do push forward or pull back. You're just specifying a vector space. Like even though these,
I mean, if the push forward should be something that lives on Z,
yeah,
and the normal bundle lives on M.
yeah. You can choose an identity. Like I said, like if these are the same, like it's kind of up to your personal taste.
Yeah.
Like you can do it in Z if you want, or you can do it over M. So yeah, I believe in my notes I wrote both anyway. So you could do, you could take TPM orthogonal complement in the pullback. The only thing that you have to think about a little bit when you're taking the pullback is you have to make sure that this vector space really does live naturally inside this vector space. So, I mean, it's not impossible, it's not hard, but it's just an extra layer that you have to put into it. Okay, so we have normal bundles, is the point. So this is for things with constant rank. Usually we're going to be thinking about embeddings, and so they're going to have certainly constant rank. Okay, and then yeah, so let's define, put a notation on it. Let's say nu sub p. This is going to be the union over P and M of these normal bundles. And I'm probably just going to decide that we have a metric anyway. Yeah, I'll say it like this. Yeah, so let's just say that we have metrics, so we don't have to mess around with stuff. And just like a little bit of a notation, if M is a submanifold, write nu of M contained in N as the nu of the inclusion. Just so it's like clear what are the two manifolds that we're actually thinking about. Okay, so here comes the first big tool. This is the tubular neighborhood theorem. This is the only time I'm going to write out neighborhood in its entirety. I hope I've at least spelled it right. So it's the last attempt I'm going to get. Okay. So suppose E from M into Z is an embedding. Okay, and we want to say that, how do I say this correctly? Can I say this correctly? Let's just say that M's closed. Let's just for now say that they're both closed. Even though I'm going to apply it in the case where they're not closed, I didn't properly look up what this is the correct statement in that case. So this is going to be a more correct statement. So then, there is an open neighborhood. I'll say n-hood, and we're going to call it mu. So I'll write it like this. So M, our manifold M, Rather, I'll say that the embedding of M, the embedded manifold, sits inside our open neighborhood U inside of Z, such that, so U admits a vector bundle structure of rank codimension of this embedding. So let's pick our dimensions again. So the dimension is going to be the codimension of M in Z. And by these numbers, I'm saying that that's Z minus M. And the normal bundle, so whatever this vector bundle structure is we have on this U, is isomorphic to our normal bundle E. So it's saying is that our nice embedding has a normal bundle, but that normal bundle can actually be realized as a subspace of this manifold that we're embedding into. So like maybe we embed this circle, and maybe the normal bundle looks like this. Right? And so maybe this normal bundle here is our subspace U, our open neighborhood U. Which just looks, so our normal bundle, we defined it sort of really abstractly as this quotient or as this orthogonal complement inside of a tangent bundle. But the tubular neighborhood theorem is saying that we can find our normal bundle actually sitting inside our Z. Like it's not on top of our Z in the tangent bundle. We can actually find it inside of Z. So that's very surprising as well as useful. Okay, so this is our tubular neighborhood theorem. And now we get to something named after one of these two people. It's called the Thom space. Ooh, I absconded with that. Okay, so let's say for V over X, a vector bundle, and let's just say it has metric. So the Thom space, THV, is defined to be, okay, well, let's take all of the vectors in V, the disk bundle, all of the vectors in V whose norm is at most 1. And then at the boundary, or depending whatever boundary means, at sort of the extent of this disk bundle is the sphere bundle, all of the vectors whose norm is exactly 1. And we take the quotient by that. And this is our definition. Just take disk bundle modulo sphere bundle. So what does that look like? So let's look at a really trivial example. So let's let V equal, say, S1 cross R. So the trivial one-dimensional bundle over the circle. Let's draw it down here. Yeah, okay, we know what circles look like. This is a cylinder on a circle. So what this is saying is take the disk bundle. Well, let's just suppose that this is already a disk. Well, okay, well, here's the disk bundle. Never mind. So let's take the disk bundle. Here's the disk bundle. So all of these are like unit intervals. All of these vectors have norm 1. All of these vectors have norm 1. So if we take the disk bundle and we want to quotient out by the sphere bundle, that means we have to take this entire circle on top and this entire circle on the bottom, crunch that down to a point. So you can crunch them up top first and at the bottom, and that looks like the suspension of a circle, but we actually have to identify those 2 points as well. So what we're getting is something that looks like, how do we draw this? Sort of like this. It looks like you take a 2-sphere. This is really bad drawing, my apologies. Yeah, it's like you take a 2-sphere, but you take the north and south pole and you push them together. So why don't I just write that out? So the Thom space of this bundle looks like the 2-dimensional sphere, and then quotient out you identify plus or minus, let's say, the third standard basis vector. So how do we draw this so that it's convincing? Somehow like this. It's really not a good picture. I've drawn this better in the past, I really have. So you can kind of imagine what I'm saying though, right? If you glue the top and glue the bottom separately, it looks like a two-sphere, then you have to glue them together. And so in general,
Is it just within the single point, or is it like double cover
no, it's like gluing at, it's like you're taking the entire upper and lower circles and you're making that one single point. And so like the rest of the thing embeds into this, and then it's just the circles that all go to one point. But like if you take the quotient map anywhere away from the sphere bundle, you're getting like a local homeomorphism between those two things. It's just the sphere bundle that goes down to this bad point. Well, it's a good point, depending on if you, well, I don't think there is any depending. The collapse point is a good point. Everybody loves this point. Okay, so in fact, in general, I mentioned suspensions. So the Thom space of, if you take X cross an n-dimensional trivial bundle, this is actually the n-fold suspension of the space X with one disjoint base point. So over here, if we had just taken the suspension of S1, it would have given us S2. But if we throw in this disjoint base point and then take the suspension, then we get kind of this weird thing happening, where you take the suspension and then you kind of have to identify the two suspension points.
I don't understand the disjoint base point here. So I kind of have like a picture in my head of what's going on. So you just have like a point disjoint from your suspension.
Yeah. So you start with your S1, and you put like another point out here.
Yeah.
And then when you take the suspension, it's like you're drawing all the lines from here to there. And then you're also drawing all the lines. Oh, no, yeah, you're right. It's not quite.
Maybe taking the suspension of like the circle and then identifying the two tips of the suspension.
Yeah. I think I just am misremembering now. Because like here you have this entire circle that you also want to crunch down to a point. So let's maybe just forget that I said this. Because
Using like the actual suspension and then identifying the suspension.
yeah, I think that's correct, but there is like another way of writing it as term as just like a suspension of something with an added base point. But since I don't remember off the top of my head right now, I'm going to refrain from writing down lies for you. So, yeah, it is more like that. Yeah, you're taking a suspension and then like connecting together the things. But if you have like a non-trivial bundle, then it's sort of like a twisted suspension. This is the idea of a Thom space, is that it's like a twisted suspension. That's the idea that I was trying to communicate. So given that we have a Thom space, so now let's go back. Let's go back to an embedding. Okay, so we had an E going from M into Z. Okay, so now what can we do? So we know that we have how do I say this? Okay, what's the best way to say this? Okay, I want to say, okay, so we've got our M, and we map it diffeomorphically onto the embedded copy. And we've got our normal bundle living over M. And over here, we have our tubular neighborhood living over the embedded copy. And we know that there is some isomorphism between these two as bundles, right? And so the normal bundle, well, at least like if you take the normal bundle and sort of shrink the fibers down to be inside of the unit disks, you could consider this to be a subspace of the Thom space of the normal bundle. There are other constructions of the normal bundle that don't use a metric, where it's kind of more natural to see the vector bundle living inside the Thom space. You're essentially just adding a point at infinity, but the metric makes a really convenient description. So the new E is sitting inside of this Thom space, this U is sitting inside of Z. And so now there's a really interesting collapse map construction going the other way from Z to this Thom space of the normal bundle. So how does it work? So you start with Z. Now you just take the quotient of Z modulo everything that's like outside of our tubular neighborhood. We just have this tubular neighborhood. We have a subspace, which is everything outside of the tubular neighborhood, and we can crunch that down to a point. Everything that's outside of this tubular neighborhood, we can also just consider, all right, supposing that, again, we identify our thing with the open disk bundle, everything outside of the tubular neighborhood would contain the sphere bundle. So it stands to reason, if you go and stare at this long enough, you're going to get that this is the same as taking the disk bundle of U modulo the sphere bundle of U. And this is, by definition, our Thom space of, what am I doing here? Well, yeah. So this is the Thom space of our bundle U, which we said is isomorphic to the Thom space of mu E. So this is our collapse map. So the real meat here is going from the whole space Z to everything, crunching down everything that's outside of our tubular neighborhood. So maybe if you go look at this picture here, here's our Z, here's our tubular neighborhood inside. So if you collapse everything outside of U down to one point, that's essentially the same as just taking like this boundary of our tubular neighborhood, crunching that down to a point, and you kind of forget that there was more stuff outside of that. So you get the same thing. So this is a, yeah, we'll call this the collapse map of E. So it depends on the embedding, but also a little bit on this normal bundle, as well as some choices that we made here, but not too drastically. And I called it chi E. Chi stands for collapse. Yeah, chi E U, I guess. Sure. And then I want to claim that, sure. Yeah, maybe I define an isotopy here. All right, so there's some nice relationships between embeddings. So if E0 and E1 are two embeddings, I'm just going to say an isotopy is a smooth homotopy. So that's just going to be an H from the cylinder M cross I to Z. So that, well, of course, H has to restrict to the two embeddings that we're interested in. And HT is an embedding for all T. So H itself doesn't have to embed the entire cylinder into Z, but at each time, at each instant T, you're getting an embedding of M into Z. So it's really a path, why don't we just say, i.e. it's a path in the space of embeddings, if you'd like to think about it that way. Where you give this space the compact, the C infinity topology, so that functions converge if they converge like uniformly, and also all derivatives converge.
So here you have the quotient algebra the diffeomorphism group of M.
In this embedding space?
Yeah.
No. Yeah, we just want to think about all embeddings, and we're just thinking about a path of embeddings. This is what we call an isotopy. Yeah. So what's my point? My point was down here, if, and I'll give a name to it, let's say E0, I don't know, double tilde, sure. If E0 double tilde E1, then not only are the normal bundles isomorphic, But we also get a nice little commuting triangle. So you have your Thom space of one of them, and this is homeomorphic via this isomorphism to the Thom space of the other one. You have your Z, and you have your two collapse maps. Let's say chi1, these should have different labels on them. E0, E1, this is going to be chi0 and chi1. So your two collapse maps are compatible in this way if you have an isotopy of embeddings. So your normal bundles are the same, and your collapse maps can be identified when you identify the two Thom spaces like this. Okay. Normal bundles. That was stage one. Perfect place to get to. Does anyone questions of normal bundles while I'm erasing the definition? Okay, people seem fine. No one's deeply offended yet. Okay, next topic is going to be really cool. This is called transversality. So I've mentioned this at least once or twice, but it's worth mentioning again. So let's look at a specific case of transversality where Z is a manifold, let's say closed, and we have two submanifolds, M, N, and these are also closed. Okay, so we say that M and N are transverse if for all points in the intersection the tangent directions along M and the tangent directions along N complete all of the tangent directions in the ambient space. So like example, yeah, let's put a box around this. So for example, say Z is R3. And, oh, I don't know, maybe like M is this sphere, and then maybe N is this line that goes through the sphere, comes out the other side. So here's one of the intersection points between M and N. So you're seeing, okay, tangent directions along N are basically just that way. Tangent directions along M are like this and like this. If you look at these three vectors inside of Z, not only are they linearly independent, but they also span, the tangent space of Z at that point.
So your definition of transversality includes that M and N, the dimensions add up to the dimension of Z?
Oh, they do not have to.
Okay, because there are some people that say that that's transversal, and if it's not, if it's just this what you wrote, then it's like a nice intersection or something. Some symplectic people are.
Okay. Yeah, I think
a bit
topology.
pissed if you call this transversal.
Yeah. A lot of different fields, like they have more specific meanings of transverse. For topologists, I believe they prefer this.
Yeah.
Because then when you talk about transverse intersection, if the dimensions don't add up to the dimension, like if they're less than the manifold,
Yeah.
transverse intersection implies that they're disjoint.
Yeah.
So it's good to have that, like, that the dimensions don't actually have to be exactly the same.
I agree with this definition, but I'm
Okay.
just.
Perfect. So we're all happy. And we write this as a horrible notation, M pitchfork N, to mean transverse. So like this is supposed to denote what a generic transverse intersection looks like. You have things that like go like this. You don't like things that aren't like this. So how about not transverse? Here's an example of something that's not transverse. Is if you have two lines that just come and they just bump at one point. So then the two tangent directions, the tangent planes in that point, we only recover this one tangent direction. We don't get any going this way. So this is not a transverse intersection. Okay. And so here's the facts. Here's why we enjoy transversality so much. Okay. Next time I draw a picture, I'll think about that. So this is something that you'd see in like your first differential topology course. So if M is transverse to N, then the intersection, the actual intersection, is a smooth manifold of dimension M plus N minus Z. So this is where like, right, so if M plus N is less than Z, you can't have a manifold that has negative dimension, so the only way they could be transverse is if they are disjoint. Right, so if you have two disjoint manifolds, this condition's automatically satisfied. Disjoint manifolds are transverse, always. Okay, there's some notes on boundaries, but I said that these are closed, and so I won't write that down. And, so the normal bundle of the intersection inside of, say, M, this is isomorphic to, okay, well, let's think about this. So this intersection is a 0, it's a point. The normal bundle of this point in M is kind of this little disk, right? It's just the two directions pointing along M. This is the same as the normal bundle of N in Z. So this is at the intersection. Right, so if you take the normal bundle of N in Z, and you look specifically at a point that's in the intersection, you see that the normal bundle of N in Z are precisely the vectors that are pointing in the M direction, or at least they're isomorphic to that tangent space. So this is kind of like codimension is preserved.
In your notation, shouldn't it be on the right-hand side, N subset Z?
Yes, that is right. That is what I was doing. Yeah. So basically, like, there's this kind of, we're preserving codimension, and this is witnessed by the fact that the normal bundles behave in this way. Okay? So this is for embeddings. It turns out you can define all of this transversality business for arbitrary smooth functions. And it looks pretty similar. And in fact, I could have just started from there. But I just wanted to motivate it with embeddings because there's something that's kind of easier to see. So suppose F to Z, G are smooth, just smooth functions. Yeah. We can still say, so F is transverse to G. So instead of saying that the manifold is transverse to another manifold, we're saying that two functions are transverse to one another. And we'll still write it with pitchfork if basically exactly the same thing happens. But you can't just say intersection. You have to be careful. You can't just say like when one intersects the other, because the domain of F and the domain of G are different spaces, right? So in order to talk about these intersection points, you have to look for all of the points of M and points in N that map to the same thing. So you're looking for all pairs, PQ in M cross N, such that F of P equals G of Q, then we have the analogous condition. So we would have that F star, so the push forward of the tangent space at P in M, plus the push forward of the tangent space at Q in N is going to be equal to the tangent space at F of P in Z. Or equivalently, because F of P is equal to G of Q, these would give you the same thing. So it's a little bit harder to visualize, but in principle, it's the same idea. And so this weird space that we're deciding is the set of pairs PQ that we're interested in, well, there's already a name for that. It's called the fibered product. So what we do is we write it like, okay, you have your domain of F, you have your domain of G, and this is how I'm writing it. I'm writing it as a sub. Normally people would put the target Z as a subscript, but I'm putting both functions just to like emphasize that we could have changed F and get a different fiber product, right? So it's not dependent just on Z, it depends really on these functions, and we're precisely just defining it to be the set of all these points.
Yeah, it always bothered me when they just put Z.
Yeah. So if you've seen pullbacks of bundles, this is the definition of the pullback. This is what you write for your pullback of bundles.
Just categories.
Yeah, this is the pullback
Exactly.
of any set, concrete categories. Be careful. And there was another thing I wanted to say. Yes, naturally this is sitting inside of M cross N. It's a subset of M cross N. Set of all pairs satisfying a specific nice condition that we specified. Okay, so given that, the analogous fact that's analogous to our, actually I'll write it right here, just so I don't have to go to the other side of the world to write down one fact. Let's go here. Fact. So if F and G are transverse, then the fiber product is a smooth manifold. So basically all of these things that are true for the embeddings case, which I am writing right here. Oh, good. That's actually a good place to write this. And it does have the right dimension, n plus m minus z. So it's very analogous to the embedding case, but it's way more general. And you have all of the same stuff about normal bundles as well. And then,
Product could be viewed as a fiber bundle, right?
not in this case. No. Yeah. I think if either F or G itself was a fiber bundle, then this would be a fiber bundle. Yeah, good question. Or more generally, if it's a fibration, if F were a fibration, then this would be a fibration as well. That's just, yeah. Pulling back fibrations is always something. Yeah, that's actually kind of true. So if one of these, there are like a large class of properties where say if this map from F to Z has that property, then the map from the fibered product to N would have that property. So you can write a little square. Where's the best place to write this square? Is probably right here. So we have M cross N over F comma G. And here's say N, here's M, here's our F, here's our G, here's our Z. I hope this is legible. So this being a subset of the product comes with projections. So we get like an F bar and we get like a G bar.
It's
So-
like a universal property.
Yeah, is pullback. Yeah, pullback comes with these as part of the universal property. So this is just, we're actually realizing the pullback with this specific construction. So if F, for example, like you were saying, if F is a fiber bundle over Z, then F bar is a fiber bundle over N. And I think it's also true, like if F is an embedding, then this is also an embedding. F bar would be an embedding as well. But if F and G are just really weird things, sort of like their pullbacks to M and G might be really weird and twisted up, but then like the fiber product kind of is unwinding it all for you. But yeah, but if F was an embedding, then you would be nice and you'd find your intersection living as an embedded submanifold of N. So that's, I think, going to come up.
Do people put the 90-degree?
I guess. Yeah, sure.
Cartesian square.
This is a pullback.
Yeah.
Daniel's being pedantic. You can write a pullback with a little half square with a dot in it. That's right. Okay.
I think in lab they call it the Cartesian square.
Yeah. Cartesian square is kind of a different word for pullback in some categories. Yeah. And what was I going to get? So there's also versions of all of these statements for manifolds with boundary. I'm going to write this down. I haven't stated this for manifolds with boundary, but you can, and I need to have a generalized version with manifolds with boundary. So if M has boundary, but let's suppose that N and Z are still closed. then if f is transverse to G and the boundary of f is transverse to G, so by the boundary of f, I just mean take f and restrict it to the boundary of M. If both of these are true, then the fiber product has boundary, and the boundary of the fiber product is going to be living inside of the boundary of N fiber product with N over the boundary of F. I should have put that on its own board because it has like an interesting consequence that I'm going to spell out. Yeah, I'll just do that. I think I need to refresh my chalk. Why? Is this, I guess this is relevant.
We did another Whitney trip.
Yeah, okay. So what does this last fact entail? So for example, suppose we have a smooth homotopy. Right, so now we have a cylinder on M. That's definitely not a closed manifold. And let's put in our dimensions like this. Suppose we have a smooth homotopy, and suppose we still have a function G going from N into our space Z, okay? So let's say that both of these manifolds are closed as well, so that it fits within that context over there. So if H is transverse to G, and say the boundary of H is also transverse to G, so what does boundary of H being transverse to G mean? It means that this is a homotopy between two functions which are transverse to G. So if we start with two transverse functions and we take a transverse homotopy between them, it's transverse to this G, then if we take this fiber product, which is starting to look a little cumbersome, this is smooth, and the dimension is, what is it? It's M plus 1 for this guy, plus N, minus Z, okay? And the boundary is going to be M cross 0, 1, so the boundary of the cylinder, fiber product over boundary H, G, N, or we can write this differently, that is not how a cross looks, as just a disjoint union of the two fiber products. So there's M on one side, well, I'll just write it like this, M fiber product with F and G, union, disjoint, M fiber product with, yeah, sure. How about F tilde with G? N. So let's say H is a homotopy specifically between functions named F and F tilde. So this assumption is saying that both F and F tilde are transverse to G, so they have their own fiber products. And then if the rest of H is transverse, then we get this whole transverse intersection whose boundary is actually the two manifolds we started with. So therefore, this thing, this thing is a cobordism. Between this thing and this thing, right? So if we started with two transverse functions, you get two different manifolds, two smooth manifolds. If we can interpolate them with a transverse homotopy, that transverse homotopy right? This is the dimension of the thing between them. That's one more than these two dimensions. That transverse homotopy gives us a cobordism between the two transverse intersections that we started with. So that's wild. I'm going to write that down as a principle, because that's sort of one of the roots of this entire discussion, is this principle that we just figured out. It's a principle. Goes like this. So a smooth homotopy apostrophe S, smooth homotopies, transverse intersections are cobordisms. It's kind of a really rough way of saying what I actually spelled out on this board, even though the writing is really bad. All right, maybe we can separate this out so it's not so horrible to look at.
So either F nor F tilde have to be embeddings, but I think it's still a cobordism.
Yeah. This is what the fiber product does for you. You don't have to work with embeddings. You still get this manifold living in this like kind of abstract place. Yeah. Ultimately, it's a submanifold of M cross N. Yeah. So yeah. Nothing in this picture is an embedding, but we still get cobordisms between stuff. Okay. So now that we have this, so if we had transverse stuff to begin with, that's all well and good. If stuff wasn't transverse to begin with, it would be nice if we could make them transverse. And indeed we can. So this is one of the meat and bones of differential topology. So given any two smooth maps, you could even make them continuous, and you can use smooth approximation to make them smooth. But we're just going to do it one little chunk, one modular piece at a time here. So these are just smooth functions. So let's say if A in M is closed with, if you have the restriction to A is transverse to G, then there is I'm going to call it a perturbation in quotes. It's really a homotopy, but you can fix an epsilon arbitrarily small, and given that epsilon, you can produce one of these homotopies that moves things by at most epsilon. So this is what I'm calling a perturbation. So there's a perturbation from F to something called F tilde, which fixes A. So the perturbation fixes A. And at the end of your perturbation, all of F tilde is transverse to G. So if you dropped this A business, what is this saying? This is saying that if you have arbitrary smooth functions, you can nudge one of them arbitrarily small to make them both transverse. The additional stuff with A is saying that if your function if your function F already was transverse on some nice subspace, then your perturbation could be made to leave that subspace alone. So for example, if you had a cylinder where both ends are transverse and the stuff on the inside is kind of random, you can just perturb the inside to make that transverse while retaining the information on both ends. So this is a very powerful function. Okay. Sorry, powerful function. Powerful result. This is super, super important for all of differential topology. So what this is saying is, right, given any two smooth functions, you can nudge one of them to make a manifold out of the transverse intersection. Yes, this is easy child's learning. Every first lesson in differential topology, when you're a tiny little baby, your advisor tells you all about this. So in other words, yeah, so how well defined is, let's say, F tilde transverse intersection G? If we just started with an arbitrary f and we wanted to nudge it a little bit to make a manifold out of these two functions, how well defined is that? Obviously, it can't be like completely well defined, because if you can homotope f so that it's disjoint from G, then your transverse intersection is empty. But you can also homotope it back so that it has an interesting intersection, right? So it's not super well defined, but how well defined is it? Well, suppose, let's see, do I even have to like explain this, or is this just kind of obvious by now? Right, so suppose like f prime are both transverse to G. Yeah, how do I say this? Okay, so if you started with an f, and you bumped it to an f prime, and you bumped it to an f double prime, so that these are two transverse functions, you still know that these two transverse functions are in principle homotopic, right? So let's start with two transverse functions which are homotopic, and see what happens. So exactly what I just said, we can take some homotopy from f to f prime, just some homotopy, and then we can apply our transverse approximation relative to the boundary. To get an H tilde going from f to f prime. But now H tilde is transverse to G. And so, right? And so what this gives us is a cobordism. Just like we had on that other board. I'm really getting annoyed by this notation all the time. But it's in my notes, can't do anything now. Okay, so we just had two transverse things that are homotopic to each other. We get two manifolds, which could be completely random, but in fact they're not completely random. We can find a cobordism by choosing a transverse approximation. Sorry, a transverse homotopy between them. Transverse approximation tells us that we can make a transverse homotopy. That gives us a cobordism between these two manifolds. And so, right, like we didn't have to start with a transverse thing. We could start it with an arbitrary continuous function from m to z. We can apply smooth approximation to it to make it smooth, then apply transverse approximation to actually make a manifold. And then that manifold is only, our choices make it only well-defined up to cobordism. So in any case, we get a function, we get a well-defined function It's always fun when you have to like really be sure that the thing you're working with is a function and not just like random noise. It actually has a well-defined output. So this is going from homotopy classes of maps from M to Z, and it's spitting out cobordism classes of manifolds whose dimension is M plus N minus Z. Right, and what do? Is we take an F. Like I said, you take an F, just nudge it so that it's transverse to G. Yeah, and then you do your transverse intersection. So M cross over our nudged map, G, N. Okay, so this is interesting, right? Given any manifolds, blah-de-blah-de-blah, you can just construct cobordism classes of manifolds by doing this transversality business.
We could extend this to a map from homotopy classes of MZ and NZ, the product of these, to the cobordisms of M plus N minus Z.
Yeah, sure. You make G a variable as well. Yeah, sure. For our applications, G is going to be a fixed thing. So I only really need to think about it in terms of this.
But yeah, you can just apply the same trick that you said. You just take a homotopy, you make it smooth, you make it transverse.
Yeah. Yeah, same. You just do both. Yeah. What else did I want to say about this? Right. You can also take pointed homotopy classes here, as long as the base point of M goes somewhere that isn't in N. As long as because then your your function on M is already transverse at that base point if it doesn't even intersect N. So you can leave the base point fixed through your transverse approximation. So you can take pointed or unpointed maps, and you still get a function. And so the question is kind of like, for which M and which Z is this function like good, right? Do we get a surjection? Do we get an injection? Like what? So that's where we're going to head next. Well, let's, yeah, sure. That's where we'll head next. Does anyone have questions, other questions they want to ask while we're sort of wrapping up that little chunk? Okey-doke. Let's see. I was thinking of trying to do this in a different order, and I might just confuse myself if I do that. So I probably shouldn't. Okay. So here's the last little ingredient we're going to need. This is the Whitney Embedding Theorem. Okay, so let's let M to the power of D be smooth. There's kind of two clauses that I'm going to mention. So if K is at least D, there is an embedding M into Euclidean space of dimension D plus K. So K, I'm taking K to be the codimension. K stands for codimension. And D is the dimension of my manifold. So as long as the codimension is at least D, you can always squeeze it into a Euclidean space. And there's a slightly other, I don't know, Wikipedia calls this the weak version. But I think it's actually a kind of a strong statement. So if M to R D plus K is continuous, so you start with any continuous function, and if K is strictly larger than D, we can perturb, let's call this F, we can perturb F into an embedding. And I don't know, kind of feel dumb because I just got these statements from Wikipedia, but I'm pretty sure there is a relative version as well, like if it's already an embedding on a subspace of F, or a subspace of M, then we can perturb it so that you leave that part alone.
Is this perturbation the same as this perturbation here? Or?
Yeah, like you can like make an arbitrarily small change. Yeah, it's really wild. Yeah, part of Whitney Embedding Theorem is that the space of embeddings is dense in the space of continuous functions for this one. Yeah. So this is our embedding theorem. Some outcomes of this that I'm not really going to spell out. So if we have K is sufficiently large relative to D, I'll write that like that. Doesn't mean that it's like a billion times bigger, it just has to be sufficiently large. Then any embeddings say E0, E1 from M, D to R, D plus K are isotopic. So that's kind of amazing. So the path, which just means that the path, the space of embeddings between these two manifolds, as long as the codimension is sufficiently large, is path connected. And then all of that stuff about normal bundles kicks in, so that the stable normal bundle is something that's well defined.
K has to be just asking, K has to be at least T plus 2 or something for this to work, because you want to essentially take.
Yeah, you don't quite want to embed the interval. Like you want to embed M cross I into like R D plus K cross I. So this, you don't want to, because like E1 and E0, they might intersect. So you can't be guaranteed to be able to embed the entire interval. But if you add the interval parameter as like an extra parameter in your codomain, then you're aiming at embedding the interval into this in like a time preserving, like you want thing at time t to go to thing at time t here. And then you just get like a family of embeddings. Yeah, I didn't work out the details to that. So thanks for asking questions about it. Trying to keep me honest. Yeah. So particularly this is saying that like, you know, each of these embeddings has a normal bundle. If they're all isotopic, that means that there's really only one normal bundle. Once the ambient dimension is big enough, the stable normal bundle is well defined. You're no longer getting like a choice of normal bundles. They're all the same up to isomorphism. Okay.
Is this notion of stability like actually like is it like a stability condition kind of thing, or is it?
The stability is in terms of like K. So like you can stabilize your embedding by just adding more and more ambient dimensions. And so the stable normal bundle really is supposed to be like the family of all of these normal bundles as a stable bundle. So I think we're gonna, depending on time, we'll talk about stable bundles in a bit. I feel like I'm kind of puttering along here. Has it been, is that clock even on? What time is it?
It's been 1 hour.
It's been 1 hour. Okay, that's fine. That's cool. We're getting there. We're getting there. So far, we've just talked about some cool differential topology. I think that's fine. There's nothing wrong with that. Okay, so what do we do? How do we do this? Okay, let's just go. So consider an embedding. Say E going from M to R, D plus K. And let's say K is sufficiently large so that our stable normal bundle is well defined. And let's say U is a tubular neighborhood, tubular n-hood. And then we have collapse map. I'm not going to try to motivate this. I'm just going to say it. Okay, so we're embedding into RD plus K. RD plus K, we can put it inside of its one-point compactification. Why would we ever want to do that? Well, that's because it's a sphere. And it has a chosen base point, this point at infinity. So we're going to take this sphere to be the one-point compactification with this point at infinity, so that our collapse map is actually a map from the sphere to the space that we're interested in. Because we at least pretend that we know how homotopy groups work. So that's kind of in the realm of things that we're pretending to be comfortable with. So then let's look at our collapse map. So we're going from S, D plus K, to basically our SD plus K without the normal bundle. Sorry. Crunch down everything outside of our tubular neighborhood. And we said that this is mapped isomorphically to the Thom space of our normal bundle via the identification of this with our normal bundle. Okay, super fine. Well, we haven't really gotten anywhere. What do we normally do with bundles? Well, we like to classify them using their classifying maps. So let's pick a classifying map for this normal bundle.
Sorry, just one quick sanity check. So the stable normal bundle is just the K class, or is it really a bundle?
Yeah, so if we're fixing the ambient dimension, then it really is a bundle.
Okay.
If we're letting K go to infinity, then yeah, you're thinking about K theory, like that is one way to...
Minus the one of the tangent bundle of M.
Yeah. Yeah. So if your M is like compact, so that it's compact Hausdorff, then we can identify K theory with stable bundles in this way. And your stable bundle that you're getting would be, the additive inverse of your tangent bundle. Yeah. Well, the tangent bundle shifted down in degree so that it is reduced. Yeah. Okay. So this is a rank K bundle. So it's classified by a map. No, we don't have to pick. We're actually given. I kept forgetting this. We're given a classifying map to the K-dimensional planes in R, D plus K. How does it work? We have a point in M. We push forward our tangent bundle at that point. Now it's an element in RD plus K. and we can take the orthogonal complement. Now that's a k-plane in Rg plus k. And so if we take gamma, this is my notation for the universal k-plane bundle in this space. I guess I want to call it tautological, actually. Because this isn't quite the classifying space. It is for like small enough CW complexes. But it has a tautological bundle living over it, where for each point here, each point in here is a k-plane. The fiber over that k-plane is the k-plane itself. Exactly. And so, oh yeah, this is Grassmannian. The Grassmannian of k-planes in Rg plus k. And so P has a d-dimensional tangent space. You push that forward with your embedding, and then you take your orthogonal complement, which gives you something that has the codimension. Yeah. And then we have our normal bundle is the pullback of this gamma k.
I've actually never seen that notation before.
This?
Pullback, yeah, I've never seen
Oh
that.
no,
That's
you
crazy.
haven't taken enough like category theory.
No, man. No.
Yeah, so I think a lot of authors call this the Gauss map. It's either the map that gives you the tangent plane or the normal bundle is the Gauss map, but this name gets attached to this classifying map for any embedding.
What did Gauss do with this?
He did everything, man.
If you look at the surfaces of R3, you could look at the Gauss map to S3, which would be the correct space.
Yeah.
He looked at the Gauss map in that case, but after all, everything got called a Gauss map.
Yeah.
It's like in principle the same idea.
It's in principle the same, and
Just
he had some note that this should not that it should work in every dimension or whatever.
Oh wow.
Yeah.
Never worked it out or what.
Wow. That was,
Yeah.
Really into this.
Yeah, you're always saying like everything goes back to Witten. Like, no, man, you got to read more Gauss. Go to Gauss. Yeah.
I mean, everything goes back to Euclid, so Euclid's my OG. Like,
Just a style question: would you ever teach like actual classifying spaces in differential topology, or would you always just go to the? Because you never need to talk about weird spaces if you just have this at the end. I mean, it's just out of curiosity.
Yeah, like would I use a different model for like my BON, or what do you
I
mean?
mean, you don't need to talk about the infinite dimensional classifying space because you can just do everything in this
Yeah,
infinite
and
dimensional setup.
if you're only talking about manifolds, right, you
Yeah.
always get some embedding. But Whitney's embedding theorem, it says like you only ever have to go to some finite dimensional
Yeah.
stage.
Like the idea is that you don't have to take a limit as k goes to
Yeah,
infinity.
so you
Yeah.
don't have to introduce like funky spaces. You
Yeah,
just
Yeah, but if I wanted a bundle over, I don't know, some cell complex with one cell in
Yeah,
each
then-
dimension, then I
if you're
can't.
not in the smooth topology, then surely.
Yeah, so for manifolds, this is fine.
Even in the complex category, you can just do this, right? You don't need to. You can just keep k finite, right? You don't need to do some weird limit or anything.
Like for CW complexes?
No, like if we're
Oh.
not CW, but like if like it says smooth, we're in like complex manifolds. Or whatever.
Yeah.
You just-
I think so. I'm not as like well versed with complex stuff. It's like really rigid, and I get scared of it. Smooth stuff is really like wavy, so it's closer to topology in my. Like whenever people talk about complex manifolds, like I always hear like they're just doing algebraic geometry or
Yeah,
something like
pretty
that.
much.
Yeah.
Or Kähler geometry. or
Yeah.
something. Algebraic.
Yeah. So in that case, I think it's even more
More rigid.
probably
I
yeah.
think the complex version is not true.
Oh, is it not?
No, I mean
Oh.
you can embed projective things. I mean, essentially,
Oh, I
like
see.
just embedding that into Pn and some high.
Oh, right.
Otherwise, the holomorphicity is just
You're right. Yeah.
way too strong to do anything.
Yeah. Smooth embeddings are like they can be relatively wild compared to holomorphic functions. Yeah. True. Did you have a question?
I was gonna ask, so does this trick also like, where you were saying, you can just do this, does it work for like the co-limit of the BONs or like the BOs, the BSO?
Yeah.
I mean, the thing about this particular construction that we're working with now is that right here I'm taking an orthogonal complement. For this particular step, I do need this to be a finite dimensional vector
I
space.
see.
Yeah. But in principle, like once the dust all clears, we're actually like taking homotopy groups of a spectrum over BO, the stable.
BO.
Yeah, where BO is like filtered by like the BONs.
Right, right, right.
So the BONs are in like R infinity, right? So I mean, this is kind of just like what we have to do to set everything up correctly.
I see.
And then it just ends up being like homotopy equivalent to some other thing, because you're taking like a limit and stuff.
That's pretty cool.
I might get to that. I'm sort of taking my time here, so I might not get to all this crazy stable stuff. All right, here we go. So now let's define the composition, this really wacky composition. So all I'm going to do is I'm going to take my collapse map chi-e, which I guess also depends on u, and it's going to the Thom space of mu e. And then if I named my map, I would have named it gamma. And let's call the bundle map gamma tilde. And so gamma tilde is Thom construction's functorial. So we get a map gamma tilde to the Thom space of this universal bundle. So this is like depending on a bunch of stuff. This is universal. This is fixed for all time. It only really depends on k. Well, nd, I guess. So let's call this composition, I'm going to call it phi. And it depends on m. And it depends on the codimension k and the embedding e and the tubular neighborhood u. So we have this big function defined by a bunch of parameters, goes from a sphere to this Thom space. So the question, how much does it depend on these things? Let's say k, e, and u. Can we kind of make it something that only depends on m if we're willing to put out like some equivalence relations on both sides? Okay, so yeah, without getting too far afield, I'm going to say that the dependence on u and e So U, there's kind of like a contractible choice of tubular neighborhoods here that give you something isomorphic to nu E. So changing U is actually only going to change this composition by a homotopy. Changing E, like I said, if you have a different embedding, then they're isotopic, and you get an isomorphism between the normal bundle, the homeomorphism between the Thom spaces, the diagram commutes. So this only changes phi by a pointed homotopy. So this really nice point that we added in at infinity, our one-point compactification, that just stays fixed. So that goes to the Thom point. So there's our one-point compactification point, and there's our Thom point, and that goes to that and never ever moves. So whenever we change U and E, these things are happening really far away from the one-point compactification because our manifolds are compact. They won't go off to infinity, and so it's not going to actually, we can do this, change it by a homotopy that fixes the base point. And so what this is telling us is that we really get, so you can take phi of m, still depending on k though, is an element of pointed homotopy classes from the d plus k sphere into this Thom space gamma k. So that's kind of, why is it a pointed homotopy? Let's see, because
you always have this point at infinity that you use in the...
Yeah. So like when we change, like maybe here's a picture, like here's our sphere, and then like our manifold embedded is like down here, and here's our tubular neighborhood, right?
Yeah.
So if we're changing U, if we're changing E to something over here,
Yeah, you always have to keep the point there.
yeah, you can do this in a way that nothing ever touches this point. And so our collapse map to here, our collapse map to here, both of them are going to be sending the point to like the Thom point.
Mm-hmm.
Yeah. So it's not going to change where that base point goes. So you actually just get something in the pointed homotopy classes of the space. So we've linked this up to something that we're pretending that we understand, which is homotopy groups. It's not just a functor. I mean, something can be a functor and still be like extremely complicated. I don't know if that would help us here, actually, to do this in the derived category. I think that would just be more complicated.
Then you don't have to worry about intersections anymore, but kind of it's horrible.
All right, so here's a fun claim. So if we fix all of our data, let's just pick some fixed data, M, K, E, U. This function is transverse to the 0 section of gamma K. So I convinced myself that this should be obvious.
It's just a submanifold of S D plus K.
What do you mean?
Because this is a submanifold of S D plus K. I mean,
The
the
M.
zero section of gamma K is just S D plus K.
Let's see, what do I mean by this? Yeah, like I'll draw the thing again. So here's our classifying map gamma and our nu. So our full collapse map kind of contains this little bit here, right? So from this diagram, you can see that, let's see, how do I say this? So what we want to do to make sure it's transverse, so the tangent bundle at a point P of, say, gamma K, what do I want to say? P, where P is in this Grassmannian. I really should introduce no notation. So the tangent point of this is just going to be the tangent space of the Grassmannian. Plus, O plus, gamma K itself at this point P. So if we have a P that's living downstairs in this Grassmannian, you have like all of the tangent directions going along the Grassmannian, but the normal directions are actually just gamma K itself. So in order to show that this is transverse, we just have to make sure that we hit gamma K, the gamma K normal directions. But of course we do. That's what gamma tilde is doing. Gamma tilde is taking this normal bundle and it's representing them as the normal directions in this total space. So over here I'm saying gamma K as like the total space of this bundle. And then over here we just have the fiber over P. So kind of proof by picture. Just a quick explanation. Right, we really only have to hit the normal directions, but the normal directions are just like by construction. Our classifying map hits those normal directions.
30 minutes.
Okay, I should get to the end of the proof anyway. I'm almost there. I was going to talk about like stable homotopy theory. I was going to do like Mumford conjecture. And then I'm like, what if we just like explain how differential topology works instead? Yeah. Okay, what else is that, moreover, notice that phi m dot 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 inverse of this Grassmannian, the 0 section, d plus k, is actually just equal to m itself. So m goes to the Grassmannian along this classifying map, but everything else, all of the u, everything that's away from m in the tubular neighborhood, that all goes into the fibers. M is the only thing that actually hits this Grassmannian downstairs.
What's phi?
Like the inverse image. So like, in fact, since this is an embedding, the 0 section is an embedding, phi inverse would be the transverse intersection. So why don't I actually make this a little more clear? Yeah. So since, so this is the 18th time I'm writing this all out because I'm too dumb to define a notation. So here's the 0 section into gamma k. Since gamma k is an embedding, so the 0 section is an embedding, so we can take the transverse intersection m cross over phi with 0 of this Grassmannian, this is actually going to be equal to like the actual set-wise pullback phi inverse as the inverse image of a function. Well, I guess I'll write it like this. Maybe this is why you were confused. Yeah, this is the function. We're taking the inverse image of this embedded manifold. And this is equal to m. So what's wild is we realized an arbitrary m as a transverse intersection of some map from the sphere to this magical Thom space. So by just embedding into the sphere, yeah, using our classifying map to go from our collapse map from the sphere to the Thom space of this over to the Thom space of this. So our embedding gives us a collapse map, and our Gauss map lets us push it forward to this Thom space of the universal bundle. Sorry, tautological bundle. So the cool question is, yeah, I'll just write this as a black box. I was trying to think about the following thing yesterday as well as today. I couldn't quite come up with an argument for it. I found some lecture notes by my advisor where he just says, if this is true, then we can blah-de-blah-de-blah. So maybe I'll defer you to his notes. So I think this was called a course, a lecture course in Cobordism theory or something. I already forget.
All of his titles are like that. A lecture course in index theory.
Yeah.
Yeah.
Yeah, he's kind of a funny guy.
His name is Johanna.
Johannes. Jonathan.
Good German.
He's a very German guy. Yes. So this is just, yeah, as an aside, a lot of this stuff you can go and read about it in these courses. They're very terse, but you can go look at it. I'm going to take this as a black box. I'm going to pretend this is true. Otherwise, things get a lot more complicated. So if anyone's going to call me out for lying, it's going to be for this. Okay, so suppose we have, what am I trying to say? So suppose M and N, let's say the same dimension, are both embedded into R d plus k, or let's say S d plus k. And W is a cobordism between them. And then there's sort of like, maybe this is true, maybe you have to make K a lot bigger, maybe this is true. Then we can embed W into not the sphere, but the sphere across the integral with, what do we want to say? Let's call this capital E. So the E of W restricted to 0 just looks like, let's call these EM and EN. EW restricted to, how do I say this? How do I say this? How about like E restricted to M? It just looks like EM cross 0. And if you restrict E to N, then you end up at the other side. And like no other boundary components of W intersect either side. So the idea is like we have M is in one sphere, N is in the other one, and then we have like our cobordism is going through a family of spheres. Okay, and so then we do the collapse map.
Wait, so we don't know if this is true?
Is it?
Is it
Black box.
I mean, it might be. I think we might have to increase K, which means that we're working with a different K, so the thing actually only really works in the limit as K goes to infinity. But in my mind, I was like, well, if we can do this for each K and then take the limit, then that's better. But
That's fine.
might actually not work.
And this is in Johannes's note, black box?
He says that if this is true, then we can continue with the theorem.
So that we can like write a paper about this.
They might have done that in the 1940s.
No.
Otherwise, yeah, sure. Yeah, I'm not sure. I should have spent more time trying to track down a reference for this. It's true. It might be in Rudiak. This is the like Rudiak. This is like the Cobordism reference. It's this big, thick book. And there's also Stong. This is the older Cobordism reference, like the original Cobordism reference. So I think if this result is anywhere, it's probably contained in one of those two, or it's not true. So then we get a collapse map for E. What is that going to do? This is going to go from SD plus K cross I to, well, the codimension of W in here, right? So the codimension of these guys was K. W has one more dimension, but so does this space. So the codimension of W in this space is still K. So we're still going to the Thom space of the same gamma K. And if we take this and restrict it to 0, then we get EM. And if we take it at 1, we get the collapse map for EN. So then this is a homotopy. Between what? Phi of M with this K. I'd like to have that K fixed. EM, UM, and phi of N. K, EN, UN. Okay? So if we had two manifolds that differ by a cobordism, then if this result is true, then the collapse maps are actually in the same homotopy class. So this is giving us a function from homotopy classes to this homotopy group. So we actually get phi, depending on k, going from omega d to pi d plus k of this Thom space. And then theorem is, I guess, if black box is true, if black box, then this is an isomorphism. So I only actually use black box to make this map well-defined, so that a cobordism class gives us a well-defined homotopy class in the target. Okay? So why should this be true? I'll just say some words real quick. Yeah, as long as k is really, really big. We always need really big codimension. So proof surjectivity, why is that? So we want to hit any homotopy class with one of these collapse maps. Well, we saw we can just take our homotopy class, bump it, make a transverse intersection. That transverse intersection gives us a cobordism class. And in fact, the collapse map construction on that transverse intersection gives us the map that we bumped to make it transverse. So surjectivity is really just transverse approximation. So why is it a homomorphism? That's actually not clear from what we've done so far. So if we're willing to change homotopy, we can say pick embeddings. Let's say EM into SN, sorry, D plus K, EN into SD plus K. Let's identify our sphere as being the cube modulo its boundary. And let's pick embeddings so that where by I actually mean, in this case, minus 1, 1. So that the first coordinate of EM, yeah, I can write it like this. So that the first coordinate of EM is less than or equal to 0, let's say strictly less than 0, and the first coordinate of En is bigger than 0. So, right, we can write this like this. So here is our x1 hyperplane. And it's like we have one of our manifolds in this half, and the other one of our manifolds is in that half. And so this is the direction that we form our composition in our homotopy groups. So I put it to you that by drawing this picture, I've made it clear that if we do the collapse map on this disjoint union, then this is going to be the composition in the homotopy group of these two collapse maps. Up to homotopy, of course. So this expression is taking like a bunch of homotopies into account. You kind of just have to look at that picture and then convince yourself. I would like more chalk. Yes, thank you. Thank you. And then all that follows is injectivity. So we have a well-defined surjective group homomorphism. Since it's a homomorphism, we can check injectivity by just seeing what's the inverse image of 0. So what's the kernel? So suppose, so how do I write this? Suppose that the collapse map for some cobordism class is equal to 0. And yeah, maybe I'll actually write a manifold here. Suppose this is equal to 0 as a homotopy class of maps from the K-sphere to this Thom space. Okay, what does that mean? Choose a null homotopy. So where this is the point at infinity here, so it takes this entire map and crunches it down to infinity. So then notice, of course, that if H1 inverse of our 0 section, I'll just write it 0 section, right? If H1 is entirely at the point at infinity, then the transverse intersection with the 0 section is just empty. And this is 0 in our Cobordism group. D. Right, so on one side we get 0. If H were transverse, H transverse, then we get a null bordism. So H, the transverse intersection of H with the 0 section is going to give us a null bordism between M to the empty manifold, right? And so M is actually 0 in our Cobordism group. Yeah, so that one's cool. I like that. So you start with your manifold whose collapse map is null homotopic. Choosing a transverse null homotopy just gives us a null bordism by all of the principles that we've already worked out.
Where did we use black box in this proof?
To show that it's well defined.
Okay.
Yeah, to show that if you vary a manifold by a cobordism, then you only vary the collapse map by a homotopy. Yeah, in the appropriate sense.
So this is kind of like a surprising result.
This is a very surprising result. Yeah, people were kind of blown away, I guess, when this happened. And yeah.
Is this the
Very
method to compute the omega g's?
This is the way to translate it into homotopy groups. And so, yeah, once it was written as homotopy groups, people like Tom went and they actually turned a crank. He didn't do it with the atom spectral sequence to start with. There were other methods that they came up with that I didn't find the time to go read about for this talk. But yeah, the point is supposed to be that this is really esoteric and hard to get your hands on. This is supposed to be relatively down to earth because it's just a Grassmannian, and we know at least the homology of Grassmannians, and so.
What is the Thom space of gamma k explicitly? What does it look like?
What does it look like? I mean, it's kind of complicated, right? You have to take your Grassmannian, which is this quotient space of O(n) plus D, blah blah blah, and then you take the tautological. Yeah, I mean, that quotient gives you automatically the principal bundle over that Grassmannian. You have to replace the fibers with actual vector spaces and then take the Thom construction of that. What else can you say? It's also if you take the sphere bundle. Oh my God. Maybe we'll talk later.
Okay.
Yeah, if you take the sphere bundle of the Grassmannian, then take the projection, and then you take the co-fiber of that map, that's also the Thom space. And there's a weird thing where like BOD, the sphere bundle over BOD is like BOD plus 1. No, it's got to be the other way around. Yeah, the sphere bundle over BOD plus 1 is the BOD. And so if you take the stabilizing map from BOD to BOD plus 1, and then take the co-fiber, the homotopy co-fiber of this map,
That's what,
then you get the Thom space.
gamma K. Interesting.
So from a homotopy point of view, that's kind of a nice description. It's at least easy to see like where the homology comes
You
from.
can at least describe it in somewhat of a nice way.
Yeah, computing the homology is actually like super easy because you have the Thom isomorphism that I didn't talk about. So you can get your hands on the homology really easily and then try to figure out stuff about homotopy from there, I think. How much time do I have left?
You're 12
Okay.
minutes.
Yeah, I'll just say one more thing then. So we fixed a k, and we talked about all this stuff with fixed k. And so all of our notation has this extra k hanging around. So I want to talk about what happens when we try to get rid of k. And then I guess I have to stop. And I prepared this part like 3 weeks ago, and I was like a different person then. Let's think about it. So let's increase k by 1. So what happens? Okay, so what happens when you take our actual Grassmannian of k planes and Rd plus k, and what happens if we increase both k's by 1? Okay, so we have k planes in this space, and we want to produce, say, a k plus 1 plane in a slightly bigger space. This is actually not so hard. We can just take this extra dimension and increase the size of our planes by that. So here's a k plane, and we just add the one-dimensional subspace spanned by this extra vector. So we know for a fact that this is not in this space, so we can add it on, get a k plus 1 plane. So if we take this map and we pull back our tautological bundle to something here, what do we get? Okay, so that's correct, yes. So what you get is, you actually get your tautological bundle here, but everything you pull back has this fixed extra piece of data. So you actually just get a trivial factor added to your gamma k. And so now here comes a big factoroonie that I leave as an exercise, say. If you take the Thom space of some bundle and you add a trivial factor to it, then this is actually going to be homeomorphic to the suspension. By this I mean the reduced suspension of the Thom space of V. So adding trivial bundles, you actually just will suspend your Thom space bigger and bigger and bigger. Okay, so what this gives us for here, so therefore if we take our Thom space of gamma k plus r, on one hand, this is a suspension of the Thom space of gamma k, and then we can follow through with this classifying map, which I don't think I named, but let's call this a sigma, as a kind of like bundle suspension map. Or rather, let's take this map. Do I want that map? No. I want this map to be sigma k. As a kind of suspension map for our tautological bundles. And now I draw a big old diagram, and I implore you to believe it. All right, this is cool. This is cool. I swear this is cool, don't worry. All right, so now, so suppose we take, I'll just write what I did here. And, so let's take our manifold, d-dimensional, and embed it into, one bigger. Let's start at k plus 1. where k is much, much bigger than d. So without loss of generality, let's suppose that this embedding actually lands us in a sphere that's one smaller. So E actually goes into Sn plus k. So we've set our thing up to be in one dimension bigger, but we've sort of said, okay, well, say we have way too much space, and we can actually isotope our embedding into a sphere that's one smaller with tubular neighborhood U. So in particular, so this is our neighborhood V. So our V is the tubular neighborhood in this, and U is the tubular neighborhood in this. So in particular, we just have this extra trivial dimension. So as a vector bundle, our V is actually isomorphic to our U plus one trivial dimension. Sorry, one trivial direction, pointing in the n plus k plus first direction. So now let's consider, I'll try to do this so it's not too terrible. Okay, so we've got our Sn plus k plus 1, and we have our collapse map to the Thom space of our normal tubular neighborhood V. And then we have our map, our Gauss map, bundle map, going to the Thom space of gamma k plus 1. Okay, and like we said, this is isomorphic to this, just because these bundles are isomorphic. And this, we have a map. We don't necessarily have an isomorphism, but we have a map going this way. This is Thom of our stabilizing map. Here we have Thom of our Gauss map for this bundle, U plus R. And then we can use our result from way over there that says that this is actually a suspension. This is also just a suspension. And this map we can fill in by suspending our Gauss map for U. And then over here, this sphere is, of course, the suspension of a sphere 1 degree lower. And I've noticed that I've replaced my d's with n's. It's easiest to just replace that with an n at this point. Sorry about that. Spontaneously switched notation, just using old notes. Okay, so now everything is n. Please forgive me. So this, now we can suspend our collapse map for, so this is the collapse map for V, this was the collapse map for U, but we've suspended it. And so the exercise for you is to verify that this diagram commutes. And it does. So you can just check one square at a time. Some of them, they're like black boxes that I've already written down. Others you might have to think a little bit. Okay, this is my last page, I swear. So now that we have this big, atrocious diagram, it's not that bad, I swear. Now we can actually make a deduction. So what does this say? Okay, so if we compose these two maps together, this composition actually is our phi of M in dimension k plus 1 for our embedding E in our tubular neighborhood V, right? On the other hand, if we go from here to here, this is the suspension of our collapse, of our Thom map of M for degree k, and our embedding E and our tubular neighborhood U. And then this is what it is, okay? So this is saying that, right, so phi of M, k plus 1, EV is actually equal to, well, maybe I want to give this a different name. Let's call this SK, is equal to SK composed with the suspension of the thing that's 1 degree smaller. Okay. Now, how do I motivate this next step? I think I just have to do it. So on homotopy classes, right, so we can always do the following. What am I talking about? No, I did define the SK. This is Tom of something, isn't it? What did I do? Sigma K is already doing that. Yeah. Yeah, I guess I just called that sigma K even though this is Tom of sigma. Yeah, you know what I mean. Okay, so in other words, what's happening? So we have pi n plus k of Tom gamma k. And then from here, on homotopy groups, we get a suspension homomorphism. So if we have a map from an n plus k sphere into something, we can just suspend both of them because it's a functor. And then we get a map from the n plus k plus 1 sphere to the suspension of this thing. But we also have a map given by sigma k star that's just pushing forward this into this thing. Yeah? Okay, so what's the point I'm trying to make then? Is that we have our omega n. So on one hand, we have phi k going to this space. And on the other end, we have phi k plus 1 going to this group. And the point is that this commutes. The point of this whole diagram is that when we write this down at the level of homotopy groups and we take the suspension, that suspension is encoded in this diagram as well. We actually just get a commutative diagram of homotopy groups, which means, in fact, we get a function, or rather a homomorphism, or rather an isomorphism. So, right, because we saw by black box that these are isomorphisms. So we get omega n mapping from phi to the limit as k goes to infinity of pi n plus k of Tom gamma k. So this limit is taken over these functions. So going from pi n plus k of gamma k, we apply the usual suspension and homotopy groups, followed by these nice structure maps that we came up with, these sigma k's, to go from this element of the limit diagram to this element of the limit diagram. And we have maps to each element of the limit diagram that all commute, and they're all isomorphisms. And so the map from omega n to this limit is an isomorphism. So we got rid of k by taking a limit. And so in fact, this Pontryagin-Thom isomorphism is actually a stable result. So if another iteration of this talk were to happen, the next step would be to take this type of picture and extract a definition of a spectrum. And then we can talk about homotopy groups of spectra. We can talk about Thom spectra, spectra that represent cobordism, other flavors of cobordism like orientable cobordism, spin cobordism. They all exist at the level of spectra. And we can also take this and go in completely orthogonal directions and talk about different kinds of spectra. How does the spectra relate to the category spaces? Why is it nicer, et cetera, et cetera. And I don't... Unitary cobordism? Is that what you said?
Unitary TQFTs or dagger categories.
Yeah, I guess. And if we talked about Mads and Tillman spectra as well, we could also talk about the homotopy type of cobordism categories, which is very deeply related to TQFTs, which are very popular in theoretical physics right now. So this is just like step one. This is step one of a really, really big picture, and it already included many, many, many interesting steps.
And this map is the Pontryagin-Thom isomorphism, that's what this is called?
This one, yeah, you could call this the Pontryagin-Thom isomorphism. So the ones that I wrote down for each fixed k, you could also consider those to be like the kth Pontryagin-Thom isomorphism. The idea, like in the old days, like you would want to just pick k huge, and then it's good enough. But then it's like, you know, people wanted to just stop thinking about a fixed k and just take a limit instead. Yeah, so what
Why do you need to do this? I mean, Whitney Embedding tells you that k can be chosen to be just the dimension of...
Yeah.
I mean, everything works in like 2D or something.
I think the like for one thing is that this is also coming down to a fixed n. Sometimes you want to think about all n at once.
Okay.
And then you're really talking about like the homotopy groups of a spectrum, like one fixed spectrum. And that way it's a ring spectrum, and so you can recover the entire ring structure just by taking homotopy groups of this one spectrum. Yeah. Yeah. So before we get too deep into the questions, I should formally end the talk there. Thank
You have 5 minutes left.
Baba booey, baba booey, baba booey. What am I going to say for 5 minutes? I don't
You
really.
don't have to, but
We do 5 minutes of questions.
Yeah.
You don't have to say anything.
Sure. Yeah, like my notes are just like pages of like defining spectra and then stable vector bundles and stuff. So it would take longer than 5 minutes.
Okay, so-
Yeah. Thank you. Yes. Thank you. Thank you.
So what exactly do you mean by stable result for this?
Just because we're taking like a limit over stabilizations, like suspensions. Yeah.
That's
So
nothing to do with stable bundles. What we're talking about, you know,
Uh,
stable result.
yeah, it kind of does.
The
There.
stable that you were talking.
Not the stable,
Not the
but
stable.
Yeah. So.
Not the Git stability. It's,
Yeah. Good question.
Because the 40s to 70s for topologists was really like the standard model theorists in physics.
It's like every week is like bam.
Yeah,
Yeah.
Exactly.
Really.
It's the math version of what the standard model theorists.
Yeah.
It's crazy.
And then once they hit the 70s, it's a lot of like really hard algebra computations,
L theory,
Al-
L theory.
algebraic K theory and stuff like that. Yeah.
I actually met like a surgery theorist at the TQFT thing. He's like, yeah, I just compute L theories.
Yeah. Yeah, that's what I was telling you. Like surgery theory these days is like you're just going to be doing like some assembly map mumbo jumbo. Like, yeah.
It's super complicated.
It is
So
very.
the main upshot of everything you just said is that we just have a nice way to think about these cobordism groups, these omega n's, as these
Yeah.
homotopy classes.
Exactly. Yeah. Yeah. You're using all of these like differential topology principles to like massage this really purely smooth thing into.
It's an actual topological.
Yeah.
Yeah.
Yeah, like the Grassmannians themselves, like they're defined smoothly, like it is a compact manifold with an actual normal bundle over it. And in principle, like you don't have to pick that as your classifying space of bundles. You can pick any other homotopy equivalent space as your base for this whole picture.
Like you're saying, it doesn't have to be a Grassmannian, what you're choosing.
Yeah, for this construction, it's sort of like it did have to be because we're using the Gauss maps.
Yes. Yeah.
So we did want that model,
Yeah.
but sort of once you kind of hit the gas into like stable homotopy land, you're more free to pick a model of your choosing.
Oh.
Like once you already know that the result's true,
Right.
it's sort of like you can replace it by homotopy equivalent stuff.
I see. Yeah, I see. And then now there's a completely other side of those. Do you have a question?
No, go.
There's another completely side of the story we're going to set. Now you're going to say, okay, instead of this, now we're just going to define a spectral sequence, and then we could just think of the omega n's as coming from that instead,
Spectral sequence.
like the atom spectral sequence or something.
Oh, yeah, I mean, yeah, that's one way to compute, but like a spectrum is sort of like a different thing. It's one of these overloaded terms. Spectrum is
Yeah,
like,
it has nothing to do with it. Yeah.
Yeah. But like once you get to this point, you can sort of start to see the shadow of how you would define a spectrum to be a sequence of spaces with where yeah, it's gonna happen.
Happens on these ones.
Yeah, we talked beforehand that was gonna happen. So yeah, it's basically a sequence of spaces xn where you get a structure map going from xn to xn plus 1. So like this data defines a spectrum because it's exactly what you need to be able to take these types of limits.
What about the actual spectral sequence, the atom spectral sequence? How does that come? How does that arise?
Oh man, it's let's see. Two years ago, I could have told you off the top of my head.
It's just this inclusion map. It gives you a filtration of whatever it comes at the end, homology,
Yeah.
and then this gives you like a double complex in one homotopy groups.
Yeah,
Like the-
I think you can think about it that way.
Okay.
But usually in the atom spectral sequence, you want to focus like at each prime p. So you'd want to p completed first, and then you get your what do you call it, exact couple out of this limit of
Wait, so
Thomas
what
spaces.
are the two differentials for the pi complex?
I mean, if you just want to study, for example, cohomology of something that is defined by these limits that you have, like a map that includes one into the other.
Yeah.
So you think of the cohomology theory of the last one, and you know that you get like the pullback maps
Oh, I
of
see.
all the inclusions, but this gives you some form of filtration of
I
the,
see.
Mhm.
and then if you have a filtration, you can define a complex.
Right.
Yeah, so that's going to like converge to your like homology. So where the atom spectral sequence is different, it actually converts to the homotopy of it, the stable homotopy. So yeah, it's kind of a sophisticated machine.
And that's just more of a computational tool for these omega.
Kind of, but also not. So the atom spectral sequence contains a lot of really important geometric information somehow as well. I want to study that this semester and find out how. Yeah. Question?
Yeah, I wanted to. I always ask this. Is kind of important, but like now, what would be follow-up topics to this talk? You mentioned a bunch near the end, and is there anything else that you want to talk about that can? Because you said this is like would be a first talk in a series. What will come after?
I'm not giving a series of talks on this.
You don't have to just like for anyone.
If anybody else wanted to, sure. How do you like actually come up with computations of these limits of homotopy groups? Because I know that you don't actually have to go all the way to atom spectral sequence. There's other methods of doing it more ad hoc, I guess. So I'd like to like see Tom's original calculations, or I think Milner maybe does unoriented cobordism groups. Also structured cobordism, so like spin, orientation, string, whatever, any tangential structure or normal structure would be a good direction to go after that. Yeah. There's like a wall exact sequence relating the unoriented cobordism with oriented cobordism. That gives you a way of actually computing them without any wild spectral sequences or anything like that.
Oh, Tom got the Fields Medal in 1959. I didn't know that. You think he got it for this stuff?
Yeah, probably, yeah. Yeah, I'm not sure, like when you talk about Tom, like he did do a lot of things. I think this is at least the thing that I know him best for, is that Pontryagin-Thom. I think Pontryagin did it first in like the 30s or something. He beat him by like 10 years, but he was like in Russia. And there wasn't a lot of
Tom
interdisciplinary.
and Pontryagin are both dead, so.
Oh yeah,
Yeah. These are old men.
yes. This is old stuff. This is really old stuff.
Which is crazy because it sounds so modern. You know what I mean? Like it just like.
That's because Waterloo doesn't have topology courses. So everything seems new.
It seems like.
Yeah. I think if Waterloo had some more like serious differential topology courses that you could take, this would be in it. Yeah. Yeah. This is classical topic. And yeah, this needs to be covered. Black box.
In a first course in differential topology.
No, in a subsequent talk in this series, someone has to make sure that black box is true or false.
Or the triple question mark. We need a proof of this.
Yeah. This thing.
Oh yeah, I guess that is the black box. Yeah.
Either show this is true or fix the argument. Yeah. That's a big gap that I've left. Yes. More questions? Excellent. Thank you.